So it was the theory of John Dalton that a atom was made up of, or matter, I'm sorry, is made up of tiny indivisible particles called atoms. Now, each atom of a particular element has the same mass, but the mass of an atom of one element is different from the mass of an atom of any other element. Now, with this theory, atoms cannot be changed into atoms of a different element by chemical reaction, and atoms cannot be created or destroyed in chemical reactions. Dalton's atomic theory, or John Dalton's atomic theory, was also that atoms combine to form multiple compounds in small whole number ratios. So that would be something like CO versus CO2. There's no such thing as CO 1.5 or anything. It's whole number ratios. Okay, so one of the theories that I believe it was Ernest Rutherford sought to determine was basically the makeup of an atom. And so there's this emerging theory known as the plum pudding model of an atom. And that was that an atom basically was this largely positive area, or this positive sphere, with negative charges kind of distributed throughout. And in order to determine whether that model was accurate or true, the setup of this experiment was to basically send alpha particles through gold foil. And the idea was that if you had these positive charge, or this kind of positive charge distributed randomly, and negative charges randomly distributed, well, then these alpha particles, which I'll indicate with the alpha symbol, what they would do is they would go straight through. And with a detection paper, or a detection material, you'd be able to see, oh, alpha particle hit here, 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 and here, and so on. And so basically there would be nothing that would be dense enough to cause these alpha particles to deflect off in one way or another. So the experimental design was like this. We have our radioactive sample that emits a beam of alpha particles. We've got this gold foil, and then we have surrounding it in almost 360 degrees, we have this fluorescent screen. And this is going to be our alpha particle, and that's supposed to be an alpha particle detection system. And so the idea is that if the positive charges within an atom, or within an atom, are kind of freely distributed, these alpha particles will all end up right here. But what was observed by Rutherford was that the alpha particles, yes, they did mostly go straight through, but then there were alpha particles detected here, here, and basically in, I don't know if I want to say a complete radius, but they were detected kind of all over, okay? And so in order for those alpha particles to have basically deflected off and ended up here, or here, or here, or here, well, there'd have to be something that was densely packed that caused them to deflect. And that gave way to the theory of a nucleus. That our positive charges were very tightly packed at the center of an atom. So this took basically what this experiment did, this EXP experiment, it rejected the plum pudding model. Because the plum pudding model had positive charges all over the place. And since since we rejected that, that gave way to this competing theory that the nucleus harbored all these positive charges tightly packed in the center of an atom. And so, sorry, I scribbled all over it. Okay, there we go. Yeah, so here what we've got, these little black dots, are where our alpha particles deflected off. So here we've got one that kind of, and then others that just bypass the nucleus altogether. Okay, so the nuclear atom, or the nuclear model of an atom, is that at the center of this nucleus, at the center of an atom is what's known as a nucleus, and what that nucleus has is neutrons and protons. Outside of that, you've got this kind of randomly distributed cloud of electrons. So you've got electrons kind of all over the place. Okay, so imagine that the nucleus is the size of the marble, the electron cloud would be the size of a football stadium. So that's kind of the scaling that you should think about there. It's huge compared to the very small nucleus. Now your subatomic particles are protons, neutrons, and electrons. They have charges of +1, 0, and -1. The masses of those relative substances, or relative subatomic particles, are 1.0073, 1.0087, and 0.000549. These are extremely small, and an electron is effectively, by comparison to a neutron and a proton, it's almost massless. Okay, now what I always like to do is I like to think about what does an atom look like and try to visualize that. The atom that I always like to pick on is Li, or lithium. Now the reason that I like to pick on lithium is because it's a great Nirvana song, but also because it's kind of simple. And I'm going to show you a couple of things about lithium. So I am pulling up ptable.com because that's going to tell me the information that I want to know. So looking on the periodic table, I see that lithium has kind of this display: 3 Li and 6.94. Okay, now that's 6.94. For the sake of this, I'm going to round that up to 7. So I'm going to rewrite this as 3, which I'm going to write that in black. I'm going to write my symbol in green, Li, and then I'm going to write my 7 down here. Okay, so these 3 different numbers, or these different things, tell you, well, different things. This 3, that is known as the atomic number. And that is going to tell you the number of protons. This right here, 7. Well, 7 is the atomic weight. And that is going to be protons plus neutrons. Now remember, the 2 substances, or the 2 subatomic particles that had mass by comparison, were our protons and neutrons. Our electrons were, I guess, 100,000 or almost 100,000-fold or 10,000-fold smaller by comparison. But I always like to build an atom and draw an atom with this information. So lithium has 3 protons. Our atomic weight is the number of protons, which we got from up here, 3, plus what gives us 7. So 3 plus, I'm just going to say x, our number of neutrons, would have to be 4. I hope that makes sense. So what I would do is I would go ahead and I'm going to draw a positive to indicate my protons, and I'm just going to draw the nucleus right now. Positive, positive, positive. Those are my 3 protons in the nucleus, and then I have to draw a total of 4 neutrons, which I'm displaying by writing the letter N. Now, lithium, as it turns out, is an element with that has no charge whatsoever when you think about lithium as its elemental state. Or in its elemental state. So if we have 3 positives, have I drawn, and I'm going to go ahead and kind of give myself a range, have I drawn any negative charges? No. So the charge of this right here, would everyone agree that it is, since it's 3 positive charges, neutrons are neutral, have no charge whatsoever, this would be 3 plus. Okay. Now, if I drew 1 electron in here, okay, that 1 electron is going to cancel out 1, or the positive charge of 1 proton. So now I'm at 2 plus. Then I draw another electron and another electron. Now I've got my element that is neutral. And we're going to go through more of these in just a little while, but I just wanted to give you a little bit of an idea of, well, what are the components, where are they, and how would you use the periodic table to get that information? All right, I hope this is helpful, and we'll proceed on in the next video.